The others are joining. Please wait. Introduce you to the system, WebEx system, where through which you are listening to us. You have options to raise questions through Q&A box, which you will find in the right-hand side. And also you have a chat box. In chat box, you can introduce yourself, or if you have any difficulty with the voice or if you are not able to see the presentation when it is being made, please type in the chat box so that we can resolve it. For the Q&A, please try to use question and answer box as much as possible. In case you are finding it difficult to write there, you can also use chat box. Series which we have started, learning stainless steel from technical experts, and in our current series which we call series 3, knowledge sharing on stainless steel for corrosion properties, selection guideline, and remedies. So we have today a panel of experts with us, which will be introduced to you in ongoing activities. First, I would like to ask our president, Mr. K.K. Pahuja, to give a welcome address.
Thank you, Rohit, and good afternoon to all the delegates. On behalf of Indian Stainless Steel Development Association, I welcome you to this session on stainless steel corrosion properties, selection guidelines, and remedies. This session is, as you know, is part of the ongoing educational series brought to you with the support of Mrs. Autocompu. And we are thankful to Mr. Autocompu for this initiative taken with us, particularly Mr. Rajiv Sherry and the today's lead speakers, which are Ms. Elizabeth Johansson, supported by Class Tiger Strand, and Mr. Yasin Al-Puzari. This subject, as we all of know, is one of the most important aspects of stainless steel usage. While we know the corrosion resistant properties of stainless steel, the extent of corrosion resistance varies widely across grades, and therefore right grade for right applications becomes absolutely important in order to deliver value to the end users. We hope that the knowledge of stainless steel corrosion properties and selection, which we'll cover in today's session, will be absolutely valuable, and this session will be benefit all of us, like the earlier sessions, which have been so well received by all of you. So thank you for joining, and over to Rohit. We can't hear you, Rohit.
Sorry, I was mute. So, to introduce Nickel Institute, which is a supporting organization for this educational series and a part of ISTA, we had Mr. Zorg, manager Nickel Institute, who could not join us due to some urgent involvement. So on his behalf, I would like to introduce Nickel Institute. To make that, I'll have 4 slides prepared to introduce Nickel Institute. Please allow me to load the presentation. Okay, so can someone confirm it is visible?
Yes, sir.
Yeah. So Nickel Institute is a worldwide association for primary nickel producers, and the mission of Nickel Institute is to promote and support proper use of nickel in the appropriate applications. And stainless steel being one of the largest consumer for nickel, where 75% of the nickel goes into stainless steel. Delivering outstanding physical and mechanical properties and other attractive properties, which we will see today. Nickel Institute grows and support market for new and existing nickel applications. They have offices worldwide, supported in Toronto, Brussels, China, Japan, and in India. We are their office, and we are partnering with Nickel Institute in delivering knowledge across the stainless steel industry. Some of their member companies, you can see the name of these companies. Jorg, who is not here, many of you know him because in the last 2 series he has been here talking about Nickel Institute. He is the responsible for market development activities in Asia market, outside Japan and China, and developing opportunities and partnering relationship for the benefit of stainless steel industry. So this is about Nickel Institute. Let me come back to the screen. Okay, so now I would like to invite Mr. Rajiv Seri, who is the Managing Director of Outokumpu India Private Limited, to give an opening remark and introduce the speakers. Rajiv.
Hello, hi, good afternoon to all in India and good morning to my colleague from Europe. And heartily welcome to all of you in this session, which is currently a very good initiative taken by ISDA and Nickel Institute to share knowledge with all the end users and stakeholders which are related to stainless steel industry. And corrosion is one of the main reasons that why people use stainless steel. And it is very important for all of us to understand corrosion a little bit more. And for this purpose, today we have our expert panel here. Our key speaker for today is Elizabeth Johansson, and she is senior specialist at the corrosion department of Outokumpu Research Center, which is located in Avesta Research Center in Sweden. By qualification, she is a PhD in Material Science and Engineering from Chalmers University of Technology. And she is working in Outokumpu R&D division since 2014. And she is a great pool of resource knowledge. Wherever we have required some support, we are always looking to her for the support. This presentation will also be done jointly with Yassin Al-Ozari, and he joined Outokumpu in Avesta, Sweden about 2 years ago as a technical graduate. So he is a person with very young age, very enthusiastic and very knowledgeable. And he has done double master's degree in advanced material engineering, specialist in metallurgy from both the European School of Materials Engineering in France as well as Sweden. So he has worked in various departments within Outokumpu. He has worked in R&D department specializing in corrosion, process development in hot rolling mill, and also technical value creation, where he is currently supporting all the customers for providing technical input for the new development or for solving issues. So we welcome to Yassin to this forum. And all of you know Mr. Klaus Tigerstand by now, who have attended previous session, and he is our guru, he is our mentor in stainless steel industry. And in previous session, he has shared a lot of nice knowledge with all of us. Mr. Tigerstand, he is MSc degree in mechanical engineering and with more than 25 years of experience in stainless steel industry, especially in technical and development side. And his area of focus are duplex steel, high strength alloys, and so on. Currently, he is heading the technical value creation heavy industry chapter and supporting all the customers globally. So we welcome Mr. Tigerstand in this forum. And we also have our own local expert, Mr. Deepak Vaidya, with us. He is with more than 25 years of experience in stainless steel industry, and he understands the nuisances and the requirement of customers in India. And he is always our helping hand for any support required in India. So welcome, Mr. Deepak Vaidya. So today's presentation, without taking much time, we will be talking mostly about what is corrosion, what are different type of corrosions, what are the effect of different alloying elements on corrosion properties, and what are the various tools available. So those tools will be introduced like ISO corrosion diagrams, handbooks which are available, and we can also learn from our past experiences in the similar projects elsewhere, and how our R&D team and technical value creation team support our customers in India to solve issues related to corrosion or for new application where they are looking for some kind of support that which is the right grade to be selected. So with these grades, With these comments, I will not take much time and give it back to Rohit so that we can start the proceedings. Thank you so much.
Thank you, Rajiv. Now I'd request our speaker Elizabeth and team to load the presentation. And Rahul, can you give presentation rights?
Already given, sir.
Yeah, I'll request the panelists to switch off their video so that we have good bandwidth for the presentation. Only the speaker can keep it on. Elizabeth, are you mute? Can't hear you.
Trying hit you.
Yeah.
Load my.
Yes. Yeah.
Yes, that was.
You can
There.
make. Yeah, you can make it full screen. Yeah.
Yes.
Yeah. Please go
So
ahead.
I hope you can see.
Yes.
Okay. Thank you. So I will start this presentation, and then Yasin will have a middle part, and then I will finish up the presentation. So I will hand over sharing of the screen to Yasin in the middle. So this presentation, the name of it is called Corrosion Properties, Selection Guidelines and Remedies. And the idea is that I will basically go through the basic of corrosion, the corrosion of stainless steel, what makes stainless steel different from other materials, the different kinds of corrosion you can encounter in stainless steel, because there are quite a lot of different types. And also talk a bit about the tools available for material selection and what to think about when selecting a material, a stainless steel material for corrosion resistance. So if we jump right in, the first question, what is corrosion? And there are several definitions of this, but one I would like to use is it's degradation of material by a chemical or electrochemical reaction with its environment. And the most basic one that pops into the head of people when they hear the word corrosion is perhaps the one symbolized by the picture to the right here, where you have a lot of sort of corrosion of carbon steel or iron. And we all know that we get this red rust appearance quite quickly on iron if you, for example, put it in water. And what is happening is that the iron is actually oxidizing, so you get iron ions. So you have an anodic reaction for that, and then you have a cathodic reaction where in this case then oxygen and water is a part of that cathodic reaction. And the basics why this happened, it's basically thermodynamic. So the iron that we have put a lot of energy into produce from iron ore wants to go back to its sort of more lower energy state of this in the form of oxide and hydroxide. So that is basically what is driving the corrosion. So there are a few ways, sort of, if you want to avoid corrosion, you can use a very, very noble material, like for example, gold or platinum or something like that. You could coat the material. You could add, if you have it in a liquid, you can add an inhibitor that sort of reduces the risk for corrosion. or you can use some kind of cathodic protection that protects the material. But what happens in the case of stainless steel is that if you have iron with over 10.5% chromium, which is the lower limit in the standards, is that chromium will react with the oxygen in the environment, or for example in water, or also in air, and will form a dense layer of chromium oxides and hydroxide. And this is called the passive film, and this is a basic reason for the good corrosion properties of stainless steel. It's very, very thin, 2 to 3 nanometers thick, and it forms spontaneously and rebuilds also if you, for example, scratch the material, so you mechanically damage the passive film. And as an illustration how thin this is, we can use this picture here, that if you think of a 1 millimeter thick stainless steel material and say that that is sort of symbolize that you can take a 10-story building, and the passive film would then be so thin that it would be sort of just a playing card, of a thin sort of sheet of paper on the top of the building. And this proves a very, very effective surface protection, because chromium oxide is very does not react with many sort of chemicals. But the important thing is to choose the right material, is that you have a material, choose a material where the passive film can be maintained in the environment that you are selecting the material for. So, another important point to remember is that stainless steel is not always stainless. It does corrode, and whether or not you will get corrosion will occur, and also the type of corrosion that you can get depends on the combination of the environment during sort of the whole service life of the material, and also the alloy composition. So now I will start going through the sort of main types of corrosion that you can encounter with stainless steel. And as you see from this picture, there are many different types of corrosion. We have uniform corrosion, pitting, crevice, and stress corrosion cracking. That is sometimes also put together in a group called localized corrosion. We have galvanic corrosion, integrator corrosion, and then we also put atmospheric corrosion in its own category, even though that has more to do with sort of the conditions where the material is exposed. So I will start with uniform corrosion. And what happens there is that in an environment where you encounter uniform corrosion, the passive film cannot be maintained anymore. It's basically sort of destroyed, and the material underneath the passive film is sort of exposed to the environment. And that means that the corrosion process occurs uniformly over the whole exposed area. So it sort of in that way looks a bit like corrosion that you would encounter on, for example, carbon steel. And this picture to the top of the right, on the right-hand side, shows sort of a very, very severe case of uniform corrosion. It appears in strong acids, so you have a low pH, or in hot alkaline solutions, so you have a high pH. So it's basically the extremes on the pH scale that can cause this breakdown of the passive film. One actually sort of, if you think about the consequences of different forms of corrosion, is that uniform corrosion is often, the corrosion rate is often quite constant for a certain type of conditions. And that means also that it can be rather predictable. So you can sort of calculate the corrosion rate and sort of figure out how long the material will last. However, I would say that this is sort of not the usual way to think about stainless steel. Usually we should use a stainless steel that is where the passive state is maintained in the environment we're looking at. So we don't want any uniform corrosion. One tool we can use to look at the corrosion resistance of different grades is this type of Isoclosion diagram. And here we have, in this diagram, we use for a certain environment, in this case sulfuric acid, we have on the x-axis we have the concentration, in this case then of sulfuric acid, and then on the y-axis we have the temperature. And all these lines represent the limit where we have a corrosion rate lower than 0.1 millimeter per year. And that is what we usually sort of, when we consider a material corrosion proof. So you can see here that the general trend, now sulfuric acid is a bit special, but the general trend is that with increasing concentration, the temperature that the material can withstand gets lower. So and then you can compare the different grades. So as long as you are on sort of below the different curve for a certain grade, then the material should be corrosion proof under those conditions. So an example of this is a failure case, an old failure case from the sugar industry, where they used an austenitic V16L type material, but they have 7% sulfuric acid, and also with some chlorides, and the temperature was 70 degrees C. And if we just mark this in an isocorrosion diagram, you see here that we are quite a bit above the isocorrosion curve for 316L. So there is no, it's not surprising that you get corrosion in this case. And in here, this was the picture here is just after 3 months. So in this case, perhaps a higher alloy grade such as an ultra 904L grade would be better. But in this case, I would also like to point out that we have chlorides here that could make conditions even worse. And we also have isocorrosion diagrams that takes into account chlorides in the case of sulfuric acid. So the effect of alloying elements when it comes to of stainless steel when it comes to the effect of the properties regarding uniform corrosion is not sort of that, is in some cases not that straightforward. So you just increase sort of all kinds of alloying element. For example, the case of oxidizing acid, like nitric acid and chromic acids, it's very good to have a high chromium content, but at the same time you want a low molybdenum and carbon content. So for example, basic austenitic grades like 304L or a duplex grade with low molybdenum content can be suitable there. Phosphoric acid is also an oxidizing acid, but perhaps not as oxidizing as nitric acid and chromic acid. There also a high chromium and molybdenum content is beneficial. So for example, the more alloyed duplex grades like 2205 and 2507, and also high alloyed austenitic grades like 904L or 254 SMO have a high corrosion resistance in that environment. What I can point out about phosphoric acid that often what is handled is technical phosphoric acid, and there is a lot of impurities in the acid which can complicate things. If you have a reducing acid like hydrochloric acid and hydrofluoric acid, there we also want to have a high chromium, molybdenum, and nitrogen content, like in, for example, 254 SMO. And then in sulfuric acid, which is a bit of a case of its own, there it has been found that copper is beneficial, and high nickel content is also beneficial, and high moly content. So there, for example, the 904L grade, austenitic 904L grade is often used. So with that, I will hand over to Yasin, I think.
Thank you, Elizabeth. Do you think it would be best if you give me control, or maybe you can just go to the next slides for me? If
you can decide. I can just.
Yes, please. Maybe you can keep it just this way. It's fair. Yes. So as water is the most widely available chemical compound, is also necessarily for all form of life. Many people believe that it can be quite unharmful to its surrounding, which is not the case in most cases, because water is never just water, but it also contains some other compounds or contaminants, and also some microorganisms. So it can be really aggressive in terms of corrosivity to many forms of metals, including stainless steel. Usually the corrosivity for water is associated with chlorides and some other oxidizing compounds like hydrogen peroxide or oxygen, and then also the pH and biological activity and of course temperature. And if we go to the next one, please. Yeah. So if we take some different types of water, for instance, we can see that the level of chloride can go from typically 10 ppm, for example, if we take the example of tap water, And according to the World Health Organization, the level of chloride should be lower than 250 ppm. So that's for instance, if we take some example of salty taste water, then it can be more than 250 ppm. For brackish water, it's even around 3000 ppm, and the seawater, it could range from 20,000 to 30,000 ppm. And another example is the Dead Sea. So the water in the Dead Sea has a level of chloride which can be around 200,000 ppm. And yeah, usually the chloride, maybe I can already mention that the chloride is the most aggressive ion when it comes to the localized corrosion, and it's usually takes a major role, as we'll see in the next slides, in attacking and starting in initiation of the pits. So maybe the next one, Elizabeth. Yes. So the first type of the localized corrosion is, in perhaps the most famous, is the pitting corrosion. And if we take a look at the image on the right hand side, usually the pitting corrosion is I would say usually initiated when we have a passive film that has some kind of inclusions or some discontinuities in it. And inclusions, or even size, of course, some cases, some scratches can play a major role in the initiation. Then if we have chloride or chloride that exists in the surrounding environments, then it starts this kind of initiation of the pit, and it starts, we have as you can see, like usually we there's a galvanic cell that is formed in which the bare material is anode, and then the surrounding area is cathode. And then we have this electrochemical reaction in which the anode keeps being attacked. So, but first, after the initiation, we're either in front of two situations. For the first one, which is the repassivation, in case the film, and that happens actually in many cases, the stainless steel has this a property of self-healing, so it repassivates. So in many cases, even if we have some scratches or so on, then the film gets repassivate, and the propagation doesn't keep on going, it stops there. And for those kind of pits, they are called metastable pits. But for the other case is in which the chlorides continue on the pit propagation, then we have this kind of as I mentioned, this Galvanic series in which there is some more chlorides getting into the pit in order to get this kind of neutrality with the hydrogen, and then this is actually a process that it drives itself, and then we are keep on going, and then the pits usually they can look like small. If we have a look from upside, they can look just like a small pits, but in fact we could be really deep into the material. So yeah, maybe I could also mention that the resistance to pitting, it's increases with increasing content of chloride in molybdenum, and also the nitrogen in the steel. And usually the resistance increases with an increase in pH. So usually for a pH around or higher than 11 in the solution. So yeah, as I mentioned earlier, like we could see just like a small attacks on the surface, but actually there is a higher propagation rate, and this process usually accelerates over time. Yeah, perfect. Then we can go to the next slide. One way to rank our stainless steel grades, it's the stainless steel grades, it's the pitting resistance equivalent, which is defined as as the percentage of chromium in the grade, plus 3.3 molybdenum, and 16% plus 16 multiplied by the nitrogen percentage in the material. So this is actually just a rough estimation to rank or to classify the resistance of the grade to localized corrosion. So if we take a look, for example, at the Moda grades, which is the 4016, so it has a PRA of 16 and also a CPT of lower than 10. And if we take some higher alloyed grades, for example, we can even see that, for example, the Forta ISTX 2507, it has a PRE of around 43, and for example, the Ultra 254 SMO, which has a PRE of 43%. So this is actually just a rough estimation to classify the resistance to localized corrosion. Yeah, the next one, please. Yes. So maybe you can also, yes. So this is the critical pitting temperature diagram. You can see here the CPT on the axis, on the y-axis, and then all the different grades and families on the x-axis. So the critical pitting temperature is also used as a ranking, only as a ranking method, and it's done usually according to the STM G115, a solution of 1 molar of sodium chloride. So basically, you can see how the different grades are performing in terms of CPT. So, for example, if we look at the classic family of the for example, the 416 or the 4404, we can see that they have a lower CPT, for instance, but that also can be the similar level to the duplex, which are the green chart on the right hand side. So the main idea here is that it gives us an idea about the critical pitting temperature, but it's in itself, it's not enough as a material selection, as other properties should be taken into account, such as the mechanical properties and the forming properties. So for example, two grades could have the same critical pitting temperature, but we need to take into account some other criteria in order to choose the right material for the right application. If we go to the next one, previous corrosion, which usually happens in some confined spaces, or even for example, sometimes during service conditions, there are some deposits that they happen during the operations in those deposits or crevices. It's usually we have some kind of some environments that they could be different than the rest of the environment, because those confined spaces, like they could have, for example, some higher chloride level and so on, and then there is a difference in the electrochemical properties, or so to say. So it actually happens in a similar level to the pitting corrosion. So usually the area in this under the deposit on the crevices, it usually act as an anodic area, but it's a very small anodic area compared to the larger cathodic area around it, and then that drives the corrosion or drives the attack, and it can result in some very detrimental results, so to say. So if we can look at the flange on the left hand side there, this one is a 254 SMO flange, and it was exposed to the seawater, and you can see that here we have some kind of blackish thing, and that's actually a rubber gasket, and those rubber gaskets can, we can have those small confined spaces in which we have this, this kind of, they serve as a drive for the initiation of the previous corrosion. And also here I could also mention that the resistance of the stainless steel, it increases with increased amount of chromium and molybdenum and nitrogen in the steel. And maybe we can go to the next one, Elizabeth. Thank you. So the engineering diagrams, so which is a very important tool to get an estimation about how a specific material, if that specific material would be suitable for a certain environment or not. And it's also just a way to predict the performance of the material in that environment. So we can see here we have on the y-axis the temperature versus the chloride level on the x-axis, and we can the lines are the limits between. Under the lines, usually we don't have corrosion for that material. If we are above the line, then we could expect the corrosion to happen for that environment. So for example, if we take an example of a brackish water which has a 3000 ppm chloride at 30 degrees, and you can see the red star over there. So then in this case, the duplex 2205, it should be okay for this application. But that's for the pitting. That's very important. But if we take, for example, for the crevice, then it's over the line of Forta duplex 2205. So then for if we have crevices, then it's not recommended to use. And on the other hand, if we take the 254 SMO, we can see that that it should be okay to use in this environment. And maybe I could mention that the engineering diagrams here is for a slightly chlorinated, it was for a slightly chlorinated environment. Yes. Other factors that could affect the resistance to localized corrosion, to both the pitting and crevice corrosion. So as we mentioned, chlorides, which are the most aggressive elements toward the stainless steel. Then of course they increase temperature in very low, so also in acidic environments, having some other oxidizing agents like hydrogen peroxide, ozone, and so on, microorganisms, the biofilm, and also the design, which is also somehow related to crevices, or stagnant solutions, weld oxides, and rough surfaces. These all are elements that could increase the risk of localized corrosion, and they should be also always taken into account. Now we'll talk about the stress corrosion cracking. So this corrosion, it usually happens when there's a combination of both corrosive environments and also when we have tensile stresses in the steel. And some examples of environments that can cause the stress corrosion cracking are the chloride solutions and the hot alkaline solutions, for instance, when we have some high pH. And it has been noticed that most cases of stress corrosion cracking usually occur at an elevated temperature higher than 50 degrees Celsius. This is a very a special case, which is this related to evaporation. So for example, even if we have tap water with chloride, so it has a lower level of chlorides, but when we have this evaporation of water, and then we have this condensation, and then we can have some built up in which there is chloride, but then over time with the evaporation, then we have this kind of buildup of chloride, and then the chloride in that specific area on the hot surfaces, it could build up to a higher level of chloride, which could result which could result in a very aggressive environment, and the material would then suffer from some corrosion. So in this case, it's really important that for example to pay attention to this evaporation on hot surfaces, in which is also related to risk of stress corrosion, cracking, even if the chloride level can be thought to be very low. Yes. Yes. Here we can see in the three small tables in different colors. We have the orange, green, and the blue, and that's how we classify our grades. And for the ferritic stainless steel, we don't have any nickel. For the duplex stainless steel, there's a low nickel, and for the ultra austenitic stainless steel, there's a higher amount of nickel. But this slide is mainly to say that, for example, if we take the ferritic stainless steel, it's less likely that a stress corrosion cracking happens for ferritic stainless steels. But on the other hand, they are prone to some other types of corrosion, corrosion like pitting corrosion and crevice corrosion, depending, of course, on the environment. So the main idea is that in order for the material selection, it's always good to have this kind of compromise between because we can, for example, gain over the stress corrosion cracking, but we can lose over some other type of corrosion. So it's always good to assess the use of the material depending on the final application of the material, of course. And yes, that's mainly my part, and I will hand over back to you, Elizabeth, for the rest of the presentation.
Thank you, Yasin. I hope you still hear me.
Yes.
Good. So I will cover a few more types of corrosion, and one of them is integrator corrosion. And what happens when we get integrator corrosion is that we have a steel that has been sensitized. So it has been heat treated and cooled to sort of the critical temperature interval between 500 and 900 degrees C, slower than sort of is optimal. And that means that you can get chromium carbides forming in along the grain boundaries in the material. And this is what the top picture on the right hand side is trying to symbolize. And if you have chromium carbides forming, that means that you take chromium away from sort of the bulk of the material. And the chromium is the alloying element that is providing the corrosion protection. So that means that you will have areas along the grain boundaries that have a lower corrosion resistance than the surrounding material. So the corrosion actually sort of happens along the grain boundaries, and that is clearly shown in the picture below, where we can see that it's eating away. The corrosion is sort of happening along the grain boundaries, and the grains are falling off the material, one grain sort of at a time. But this can be mitigated by having a low carbon content in the steel, and if you don't want the carbon content, a high carbon content for other properties, almost all grades today have a low carbon content. Or you can stabilize the material by adding titanium or niobium. And these elements or alloying elements are more prone to form carbides than chromium. So that means that instead of chromium carbides, you get titanium or niobium carbides, and that leaves the chromium in the material to provide the corrosion protection. And today, intergranular corrosion is rarely a problem with modern low carbon stainless steel, at least not in the way that it was many years ago, when this was sort of became a critical issue when you were welding materials. And then I will also touch a bit on the issue of galvanic corrosion. And this is can occur if you have two metallic materials that are in contact with each other, and you have a conductive liquid, so they are sort of in electrical contact with each other, and that in that case, the lower alloyed material will corrode and corrode faster than it would otherwise, while the higher alloy grade will remain unaffected. And basically, stainless steel is in most cases the most noble material. So that means that you will get corrosion attack on the other material, for example, on carbon steel. And the top right picture shows sort of a classic case where you have a large surface of stainless steel, and you have a smaller part here. This is probably some galvanized stainless steel that you have put on this stainless steel, and then you will get corrosion on this galvanized steel. And the smaller the area of the less noble material is, the faster it will corrode. And of course, this type of effect is also used to protect material. For example, on the bottom picture here, you can see a ship hull where you use sacrificial anodes where you use this effect to protect the hull of the ship. One thing that I would like to point out, and something that we get questioned about, is what happens if you put stainless steel with quite different corrosion properties together. Will you get galvanic corrosion between those stainless steel? And this is usually not a problem between the stainless steel, because it's basically sort of the passive film is quite similar on the steels. But this also requires that you have chosen that both material needs to be in the passive state. So both of them should be corrosion resistant in the environment where they are exposed. Because if one stainless steel is not one of the stainless steel is not corrosion proof, then you could get a galvanic effect. And one way to show sort of the difference in nobility or is to look at the corrosion potential of different materials. And it's important to point out that this is this kind of cereals will be sort of is unique for each environment, basically. But then we can see here that we have carbon steel and zinc quite low, and then we have the stainless steel grades in their passive state that is quite high in corrosion potential, and also we have nickel-based alloys that is a bit higher than stainless steel, but not much. So that is usually no problem either to have a passive stainless steel with a nickel base alloy together. And then on the top we have materials such as gold, platinum, and graphite. And then the last topic here is atmospheric corrosion. So that is corrosion that occur when you expose stainless steel to the atmosphere at an ambient temperature, whatever that ambient temperature. It can be indoors, it can be outdoors, and then it can be really cold, or it can be really hot. And the temperature is one factor that affects the risk for atmospheric corrosion, but you also have the humidity. You have atmospheric contaminants such as salt that you can get, for example, if you have stainless steel close to the sea, or also in colder climates where you use de-icing salts on roads. That could also be a source of salt. And atmospheric corrosion is also very dependent on what kind of surface and surface roughness that you have on the stainless steel. Stainless steels are generally very resistant, but each sort of environment needs, you need to consider each environment and select the right stainless steel. And on the right hand side you have pictures of what atmospheric corrosion could look like. It could be, if it's really bad, it could be sort of that you see real pitting on the material, but often it can just look sort of very discolored, and you have this type of sort of brownish stain on the material that is called T-staining. That can often be removed with sort of cleaning chemicals. As I said, the surface roughness is important for atmospheric corrosion, and this picture just shows the influence of that, where we have a hot rolled surface that is quite coarse and have a high surface roughness value, and we compare that to an electropolished surface, which is extremely smooth. And this was a 10-year exposure of steel grade 304, so an austenitic grade, and it was exposed sort of in the urban atmosphere, in the marine atmosphere, and also in 2 different industrial atmospheres. And you can clearly, you could clearly see the difference between the hot rolled, the coarse hot rolled surface, and the very smooth electropolished surface. So specifying the surface roughness is almost as important as selecting the right steel grade when it comes to atmospheric corrosion. And this is a typical example where we have railing with Supra 316L, so austenitic grade, near a beach, where you can see here that one of these parts is much less affected by corrosion than the other part, and it could have to do with surface roughness, but it's also affect here that this part is turned upside, so the rain can get to it and run off and remove any, for example, chloride from the surface. And one subject that I would also like to touch on is the subject of carbon steel contamination, which is basically when you have tools made of carbon steel that could get sort of on the surface of the stainless steel. It could be that you're dragging sort of something with carbon steel over the surface. It could be that you're using something to lift the material that has carbon steel. Or in this case, we have on the right-hand side, this weld has been brushed with a carbon steel brush and not a stainless steel brush. And on the other picture, we have just left a pair of pliers on the stainless steel surface. And if these surfaces then get wet, you will have this very sort of red rust appearance on the steels. But this is basically the carbon steel that has been left on the stainless steel that is corroding. And in most cases, the stainless steel is quite unaffected underneath. So sort of cleaning chemical for stainless steel would remove something like this. So material selection for stainless steel. There are some tools that you can use, and some of them we have showed here today. First, when it comes to uniform corrosion, the Isoclosion diagrams are a very good source. And we also have sort of the same information as tables. And those you can find in our corrosion handbook. It's important to add safety margins and to consider sort of any variations in the environment. These corrosion tables and isocorrosion diagrams, they are also available online. One tool that is easily overlooked is earlier experience of different materials, because often for us it can be quite difficult to give sort of really good advice for a specific environment and process, because we don't sort of know the in and outs of the process. So if there is earlier experience, and especially with another stainless steel, that can be very, very important sort of input. And if further sort of assistance is needed, in Outokumpu we have this technical value creation team that supports our local sales teams that tries to assist, and if needed also the R&D within Outokumpu will of course be assisting. So some things to remember is that corrosion proof, with corrosion proof, it means that we have a corrosion rate less than 0.1 millimeter per year. Any impurities in the environment may affect the corrosivity. All the data that we have, for example, in the isocorrosion diagrams, this is mainly impure chemicals. So if you add other impurities or other additions to chemical, that could affect the corrosivity. It's always important to consider startup and shutdown periods or any other sort of extremes, because even though the periods of time can be very, very short, it can be enough to cause sort of real damage to the stainless steel. If you have, for example, very high temperature, short time, that could be enough to initiate corrosion, and maybe it will not be able to recover when you lower the temperature again. Any cleaning processes and the chemicals that are used for cleaning should also be considered. And there it's especially important to follow sort of instructions if there is sort of special chemicals used, so they are handled in the proper way and rinsed away once cleaning is done. Leaving some cleaning chemicals can be quite aggressive, and leaving them for a longer time that is recommended can cause damage. Deposits is also important to consider. So if you have, for example, a tank where you have deposits forming on the bottom of the tank, the conditions can be much more corrosive than on the bottom of the tank compared to sort of the rest of the tank. And it's also important to remember that there are cases where high alloy grades are not always the best choice. And one thing that I would like to add here is that stainless steel should, when it comes to corrosion, should be considered as an either-or material. So you don't choose a stainless steel that will corrode slowly. You should always choose a corrosion or a material that you know is will remain passive and remain corrosion resistant. And that is sort of a bit of a different approach compared to, for example, carbon steel. So, as I said, selecting the right grade. So you should select the grade where you do not expect that any corrosion will occur. Know your environment and sort of the extremes of the environment. And the corrosion handbook is a very good tool for selecting the appropriate grade, or at least sort of give you a first hint of what grade can be appropriate, and also that chlorides is the main thing to look out for if it's perhaps not in acid environment, but otherwise that chlorides is basically the cause of most problems with stainless steel and corrosion. So I think that was my last slide. So thank you for listening. Both me and Yasin. I'm talking for him now, but
Thank you, Elizabeth.
So should we proceed for Q&A now?
Yes, Deepak, please.
Okay. Thank you, Elizabeth and Yasin, for the wonderful presentation. We have a couple of questions from the participants.
Deepak, sorry, can we go back to the original screen right now?
Yeah, so Elizabeth, can you go to the original screen, please?
Stop sharing option.
yes, I will try to. I stop.
Yeah, perfect.
Perfect. So I'll go. I have noted the questions that have been put by the various participants, either in Q&A or in chat box. The first question that we have is from Mr. Ghosh, and his question is, how do we maintain passive environment during fabrication of?
Sorry, I didn't hear the last part.
Okay. How do we maintain the passive environment during fabrication of stainless steel? Elizabeth, you explained about maintaining a passive layer in the beginning. the chromium oxide passive layer. So the question is related to that how do we maintain passive environment during fabrication of stainless steel?
I mean, mainly if we talk, for example, about forming, that is usually no problems. Then we have, I mean, you do that in sort of normal air, and you may add some grease or something to the material. But you basically have the passive film still there. With welding, we will of course add heat, and you will get a weld oxide along the welds, and that means that you have you basically have some kind of protection layer still, but the protective film that you have is maybe not optimal. So there, of course, we recommend that you pickle your welds to restore the passive layer and the corrosion properties. And I guess also that is the recommendation, for example, if you do hot forming. I don't know if you, Claes, have something to add.
Perhaps what can be added, of course, is mainly connected to the welding that is critical, that you get the oxide scale and chromium depleted zone. So in addition to pickling, of course, mechanical descaling is possible as well. But what is very important there is to really remove this chromium depleted zone in addition to the oxide scale, to be sure that you can restore the surface, and therefore it's often better to use pickling, as Elizabeth pointed out, or even a combination of mechanical descaling and pickling to make sure you can restore the properties there.
Thank you. The next question is, what is PRN in austenitic stainless steel? I understand they are asking about the PRN number of austenitic stainless steel. For which service requirement should the PRN be mandated? What is ideal PRN for austenitic?
I don't know if I quite understand.
Elizabeth, can you see the Q&A box there? You can actually see the question there if you're able to open that.
I looked at for that in the beginning.
Yeah, Elizabeth, they want to know about the PRN range of austenitic stainless.
Yeah, so basically for austenitic stainless steel, as you can, if you remember Yasin's picture there, basically you have the range for PRE values for austenitic stainless steel range from from our standard austenitic grade 3 or 4 type with a PRE value of 18, PRE-N value of 18, up to our highest alloy steel is our Ultra 654 SMO that has a PRE value of 56. So the PRE or PRE-N value has a large sort of span in our austenitic grades. And basically you have almost the same span in our, for example, our duplex grades also. So I don't know if that was an answer to the.
I think that was the question. So it's 18, starting with 18 in 304, roughly around 24 in 316L, and PRN in austenitic can go up to 56 or 64 SMO, which is the highest corrosion resistant stainless steel known as on date. Thank you. And the third question I have is, is pH greater than equal to 11 ideal for hydro testing during pipe manufacturing and after final inspection? And the second question together is, can a pH of 9 to 10 used lead to acidic corrosion?
No, if you start with the last part, 9 to 10, that's too, I think it's too low pH to have sort of get uniform corrosion on the alkaline side. And I think you at least maybe need a pH of 11, 12 or something like that. And I have never heard that people are using higher pH for hydro testing. But I mean, you shouldn't, if you do it hydro testing with the right, have control of the water, there shouldn't be sort of much issues. The issues with hydro testing, if you have water that you maybe have a biological activity, so and you leave it together with some chlorides in it. But I guess theoretically you could get some cases it could be safer to have a higher pH. But I have never heard that sort of you want to adjust the pH to have for hydro testing.
Okay, and the next question that we have is, when austenitic stainless steel flanges are bolted with galvanized bolts or nuts temporarily, is there a potential risk of galvanic corrosion?
Yes, there is certainly a risk for galvanic corrosion on the galvanized parts. But if it's, there shouldn't be any risk for the stainless steel. And then I guess if it's just temporary, maybe that's a risk you could live with if you then want to change the galvanized part to stainless steel parts. But especially in this case, if you have bolts and nuts that are much in galvanized steel, that are much sort of the surface area of them is much smaller than for stainless steel. So that will, of course, increase the corrosion rate and the risk of corrosion.
Thank you. So the next question we have is from Johansson Left, and they want to know which is more corrosion resistant, nickel or nitrogen content. So what adds to?
Hey, yeah, the nitrogen content in stainless steel, we add nitrogen, that has mainly a beneficial effect on the localized corrosion resistance, so like pitting and crevice corrosion. And then you have the nickel content. The reason why some grades have higher nickel content, that might not have to do that with we want them more that adds so much to corrosion resistance, but that is also to get the right sort of phase balance and sort of from metallurgical reasons. But in general, the nickel, where it's really beneficial, is that if you activate the material so that you get corrosion on the material, that then you have a lower corrosion rate or dissolution rate, since nickel, like nickel-based alloys, they are also sort of nickel is used for or is more corrosion resistant. So you get this lower dissolution rate. So for example, if you have crevice corrosion, you have a higher nickel content than if you get crevice corrosion. The propagation rate could be lower if you have a higher nickel content.
Perfect. So the next question is which coating would help on stainless steel in avoiding galvanic corrosion from hostile media? I understand they want to know that if they are using stainless steel and galvanized stainless steel together, so should stainless steel be coated? And if yes, which type of coating can be used?
I'm not sure about galvanized steel. Do you know about this class? I
No,
know that if you have, for example, a weld and carbon steel and you want to paint the carbon steel, it's important that you also paint a bit on the stainless steel. So you sort of separate if you have a damage in the coating. But I don't know how you handle that with galvanized steel.
No, I don't have any experience of that either, actually, specifically for a galvanized steel, if you should. Yeah, no, sorry, I don't have that. That is only for plain carbon steel where you add in typically epoxy coating or something that you should coat over the stainless steel and the weld joint as well there. But if you have a
But I guess that could also work for a galvanized.
Yeah, I guess because often you have like zinc or other protection, cathodic protection within with the code itself. So I guess that should work as well there.
Yeah, and I guess maybe you can then paint yeah, part of the stainless steel and also on the galvanized steel to separate.
Yeah, you're right.
Those
Maybe
surfaces.
you should code also the other side there to make sure if it's a galvanized steel there that you code over both there. But I don't have any experience of that specific situation.
Okay, what we can do is we request the person who has sent this question to mail to us, and we will see if we can find more details and get back to you later. The next question is from Mr. Khurana. He says, we know chlorides are problematic for stainless steel, but what about fluoride or fluorine content? We use a lot of chemicals that contain fluorine, for example, hydrogen fluorine and thionyl fluoride.
Yes, I mean fluorides all sort of halogen ions have the potential to have the same effect when it comes to pitting, and when it comes to hydrogen fluoride, that is a very very aggressive acid to stainless steel, just like hydrochloric acid is there. So there, the window where you can use stainless steel is basically very, very narrow to low concentrations. But then sort of the relative effect of, for example, fluorides and bromides might not be exactly the same as chlorides. But I would say that you can, when it comes to pitting corrosion, you can at least use the chloride, for example, the chloride engineering diagrams as a starting point for the material selection.
Okay. The next question is, kindly explain the role of nitrogen on stainless steel, because we generally avoid the nitrogen content in carbon steel, plain carbon.
Yes, so this is it's quite a complicated area, but basically the nitrogen, the effect of nitrogen on pitting and crevice corrosion has to do with sort of what happens at the sort of in the passive film when you have chlorides in the environment. So I think that I think it has to do with both molybdenum and nitrogen, sort of how it interacts with the chlorides that are harmful to the passive film. I don't think I have sort of it in my head right now exactly what happens, but that's the sort of theory behind it all. It's and as I said, it's the same with the molybdenum also.
Okay, the next question is from Mr. Sachin. Is corrosion handbook available online? No, it's not there. We have only hard copy. You can write to us and we can send you a hard copy of that. The next question is from Mr. Ashish Apte. For a tropical country like India, which will be most preferred grade for coastal structure fabrications, which have a longer exposure to surroundings? So, Clash, you would like to answer this? You're quite experienced about India.
Yeah. I mean, it can be very corrosive if you are close to the sea, and you really need to consider the specific location and how affected you are by airborne chloride coming in from the sea. Additionally, it's about how, if you have a direct exposure or if it's sheltered in some way, can influence as well. But in some cases, if you are very close to the sea with direct contact with high content of airborne chloride, it could be that you need to go up to the very highest corrosion resistant grade, like the 6 moly austenitic grades or the super duplex grade. And in some cases, you can go down one step there, but that needs to be carefully assessed from case by case there. But very close, you need to be at the highest possible corrosion resistance level there, I would say in general.
Correct. And this is what we have observed, like in different applications in India, coastal areas, we have seen that even 316L gets corroded. And another problem that we have in India, people have been using duplex. And in some of the applications, if we see at the coastal areas, the temperature itself is 45 to 50 degrees centigrades. So I have seen in some of the cases related to the tanks or something, sometimes due to this high temperature and high chloride levels and some, you talk about crude application, high sulfur crude coming up, we have seen that even duplex 2205 is not enough and we have to use super duplex 2507. Surely not P04 and 316. Okay, and the next question is whether rainwater or rusting of material can lead to stress corrosion cracking once the material is used for some drawing application. So Elizabeth or Yasin, anyone can answer.
Yes.
This is related to corrosion due to rainwater.
Yeah, and stress corrosion cracking, I think.
Yes, correct.
Yes. With rainwater, there is no chlorides in rainwater. So, I mean, then basically you need the chloride from somewhere else. And it could be that a classic example, if you have some kind of insulation that contains chlorides that you sort of then leach out and they get to the surface. But no, rainwater shouldn't be any problem otherwise.
Another question we have is consumption of stainless steel in India in non-industrial applications is majorly in J3, J4 grades, with 430 having higher levels of chromium as compared to J3 and J4 grade, can we suggest 430 grade as an alternative material to the fabricators? So, do you have any idea about this, Elizabeth or Claes? About this grades J3 and J4?
I know that we have done some corrosion testing on these grades a long time ago, and basically they have lower corrosion resistance than, for example, 304 for L and 316L. I'm not quite sure if 430 could, in some cases, be quite similar in corrosion resistance. But the thing to consider there also is that, if I remember rightly, those J3 and J4 are austenitic grades.
Yeah.
So perhaps it's the forming properties that will be the largest sort of hurdle if you want to change to a ferritic grade, because the forming properties will be quite different for a ferritic grade.
Yes, I can share additionally. Somewhere in 2007 and 8, we conducted some tests in Tornio on this J4 grade 1% nickel material, and thereafter actually it was for indoor like utensil applications, and the problem that the people were facing was delayed stress corrosion cracking and some deep draw issues and some polishing. So we tried to develop some material by enhancing the properties of good. Some other type of manganese was used, and some copper was added, which could overcome those issues. But if you do all that, then the cost increases, and it is as good as 304 or something. That's, so as Elizabeth says, that it need to be case to case basis. You have to look at for indoor applications what you're using, and so those things need to be looked at. Okay, the next question I have is related to slide number 8 that Elizabeth you have presented. The question is, can we see SS321 grade ISO corrosion curve also?
So,
is it available?
What curve was he asking for there?
For SS321, I think we have not. Can you go to slide number 8? I think then
Yeah, I
can find what was in slide number 8.
Trying to.
Rahul, give her the presentation rights.
Necessary.
So slide 8. But what grade was it for asking about? 3?
321. SS321.
No, I don't think that we have for 321. But that should be. Let me see. I think that is because when it comes to our isocorrosion diagrams and tables, we do not have the resources to test every single grade. So, for example, all types of 3 or 4 that are available. But I think that we say that for 321 you can use the 304L 4307 curve. So that you have here. So you can basically use that one. So if I just quickly share here my yeah, so for 321 you should be able to use this 304L 4307 curve. Yeah, and that goes for I think all the isocorrosion diagrams we have.
Thank you. So the next question that I have is, what is the impact of nitriding on corrosion resistance?
I think that in some cases we have actually seen a positive effect of nitriding, because you get up sort of local nitrogen content. But I'm not sure how far you could take it before you get, because you still need to have sort of a proper passive film in place. But but compared to, for example, putting carbon into the surface, nitriding is definitely better if you want to achieve a sort of harder surface. But I would say that you should evaluate according to sort of the environment you want to use it in, and ensure that you have the right corrosion properties also after nitriding.
Okay, the next question is, what precautions to be taken if carbon steel and stainless steel are to be stored at the same location?
I don't know what to say, Claes. Do we say that you should have basically two different sort of buildings if you have them inside?
Of course, that would be the best if it's possible. But if not possible, at least to make sure you're using different tools for stainless steel and carbon steel, so you will not contaminate the stainless steel from the carbon steel. And one thing could be with a forklift, for instance, when you have the forks with carbon steel, and you can easily damage the stainless steel if you are handling it in an appropriate way to make sure you have a protection in between there, for instance. So there are easy things, but as you said, Elizabeth, the best is, of course, if you can keep it totally separated from each other.
Yeah, Rohit here. Actually, just to update the attendees, is that the series 4, the upcoming series, is exactly on these aspects, where the right practices to improve fabrication quality and guidelines for handling, storage, and transportation of stainless steel and its products will be considered. So please join in the next series also. Please, Deepak, go ahead.
Okay. So the next question is from Mr. Jagdish Deshmukh. He says that confirm the best material for seawater applications.
Basically, for seawater application, we recommend our Dupex grade 2507 super Dupex grade, or our super Austenitic grade 254 SMO. Right. There are instances where you need even higher alloy grades, and there are instances where for seawater handling, for example, if you have tube heat exchangers that is handling seawater at high temperature, where basically no stainless steel will suffice. And there are also, if you have colder seawater, and perhaps also if you have more brackish seawater, where you could consider lower alloy grades. But I would say that 254 SMO and 2507 are the ones that you should sort of first consider for seawater.
So the next question is, how sulfur and phosphorus affect the surface of stainless steel?
Maybe Claes is better at that, because that is, or if is it sulfur and phosphor in the stainless steel?
So it is
as
not...
an alloying
It is
element.
that there are contaminants in that respect that would reduce the corrosion resistance. if it becomes too high.
Yes.
Okay, the next question that I have is any difference between SS316 and Supra 316?
What do you say? SS316 and Supra?
316, are they same or are they different?
I mean that if you mean a 316,
Yeah, I can
L,
answer that.
yeah,
I can
maybe
answer
you
that.
know
Yeah, so when you say 316 or 316L, you are selecting the composition from ASTM, ASME, or BIS standards. Within Autocompo, what we are producing is surely according to those specifications only. Our material conforms to those specifications. So in large, yes, Supra 316 and ASTM or ASME 316 are same. But with the experience, we try to harmonize or fix our composition in a way to give it a better life. So in large scale, they are same. But yes, Supra we use for material that we are producing within Autocompo. The material can conform to ASTM and SME. Okay, and there is a question related to alloy 625. Of course, we are not producing it. So they say that if the gasket someone is using is made out of alloy 625, should the flange be also of same material?
If they're talking about the risk for galvanic corrosion, I think it would be quite okay to use a high alloy stainless steel in the same sort of together with the 625. And I guess otherwise it depends on what corrosion properties that you are looking for. 625 is not necessarily better than stainless steel in all environments.
Okay. And there is a question that according to Copson curve, when the nickel content is around 8 to 9% in stainless steel, then it shows very low resistance to stress corrosion cracking, while ferritic stainless steel have excellent resistance to stress corrosion cracking. Please explain.
Yes, it's basically that it's the austenitic microstructure that is more prone to stress corrosion cracking. So that means that ferritic grades in general have a good resistance to stress corrosion cracking. But also when you go into the super austenitic grades, we have seen that those are also better in stress corrosion cracking. And they typically have a higher nickel content too. And nickel-based materials are also very resistant to stress corrosion cracking. So it is that combination of austenitic stainless steel with 8, 9, or say 8 to 10% nickel that is very prone to stress corrosion cracking. But it does not only have to do with the nickel content, since also duplex grades are quite resistant to stress corrosion cracking, and they have a lower nickel content. So that's unfortunate that it means that the standard austenitic grade 304 and 316 are especially prone to stress corrosion cracking.
Perfect. So we have a couple of questions which are related to welding and issues related to welding. I'm not taking them up. We can cover them in the session where we are going to talk about the right welding techniques for stainless steel. So sorry, I'm missing all those questions, and more or less, I think that covers many important. Only thing which I have left is, as I said, is welding and some related to additional fabrication and handling of stainless steel. And requesting all that if you have more questions related to corrosion, do send us an email, and we will try to answer them separately to suit your application and questions.
Yeah, thank you, Deepak. So it's over, Deepak? Can I go
Yeah,
ahead?
from
Yeah.
our end, it is.
Yeah. Okay. So I think all the questions has been taken up. Some of the questions, as Deepak very rightly said, in the end is related to fabrication and welding. So I welcome you all for the series 4, which will be happening, right practices for fabrication, handling, storage, and transportation of stainless steel and its product. With this, we have come to the end of the session. First of all, I would like to thank the speakers, Elizabeth Johansson, Claes, who has been here for last 3 series, and Yasin for giving inputs on corrosion aspects of stainless steel. We would like to, on behalf of ISDA and Nickel Institute, I would like to thank Outokumpu also, Mr. Seri, Deepak, for helping us conducting this learning educational series. And I would also like to thank all the listeners, all the attendees who have joined us and have been a part of this series for last 4 times. This is the 4th series. So we look forward to the next series, and we welcome you again on these aspects. As very rightly said, you can write to us if you have further questions. We'll either directly to the speaker or Deepak or to the Outokumpu India, or to us at nisda@gmail.com, and we'll be forwarding it to get you the right answers. So thank you all. Thank you very much. With this, I officially close this session now.
Thank you very
Thank you,
much.
Rohit.
Bye bye.
Bye.
Thank you very much.
Bye-bye.
Bye.